Now let's study angular SHM and its equation. Till now the cases which we have studied are the cases of simple harmonic motion in which a particle moves in a straight line. Now whenever we talk about a rigid body which is pivoted about an axis of rotation, in that situation the body can also oscillate, and such oscillations are called angular oscillations, and if some specific conditions are satisfied, these are termed as angular SHM. Like if we just talk about a simple pendulum, we can state, obviously for small angles the bob will be executing SHM in a straight line, but in this situation if we talk about the string of the simple pendulum which is also oscillating, and if we talk about the angular displacement, say for amplitude of bob, its angular displacement is phi, and for a smaller angle the angular displacement is theta, which is less than phi. So we can state the particle is executing SHM and the string will be executing angular SHM because it is following the same rule which the particle is following. So we can state, if we talk about the equation of motion of bob, then it can be written as y is equals to a sine of omega t plus alpha. That is a general SHM equation for a particle executing SHM. Here y is the displacement of bob from mean position at any time t. Now in this situation, if we talk about the angle corresponding to the position y, say it is theta, then we can write here y is equals to L theta, and amplitude of oscillation can be written as L phi. Here phi is the maximum angular displacement of a string from the equilibrium position. So here phi is also termed as angular amplitude of oscillation. Now in this situation, if we substitute the value of y and a here, you can see what we are going to get. It will be L theta is equals to L phi sine of omega t plus alpha. Here L gets cancelled out and we get theta is equals to phi sine of omega t plus alpha. This is the equation which is giving us the angular displacement of a string, or even with respect to suspension point it can be written as angular displacement of bob as a function of time. This equation we call equation of angular SHM of a string, or even we can also use this for bob. And if we find out the angular speed of bob during oscillation, so you can see angular speed theta dot, which can be written as d theta by dt. It can be written as phi omega cos of omega t plus alpha. Here angular speed we are not denoting by omega, as omega symbol we already reserved for angular frequency of SHM, and here the value of omega is given as root of g by L, which remains constant during oscillation. And here this theta dot, or angular speed of bob, is basically the radian per second rate at which the bob is oscillating. Now if we find out the angular acceleration, which is theta double dot, which can be written as d square theta by dt square, it can be written as minus omega square phi sine of omega t plus alpha. Now if you just substitute the value of theta from here to here, you can see we'll get theta double dot is equals to minus omega square theta, which can be written as d square theta by dt square plus omega square theta is equal to 0, which is a familiar equation for all of you. And here this is written as basic differential equation for angular SHM. For linear SHM or translatory SHM, we use d square y by dt square plus omega square theta is equal to 0. So we can state when a rigid body is under stable equilibrium due to some torques acting on it, and if it is displaced by a small angle theta, then if we calculate the restoring torque on body, if the restoring torque on calculation, say we are getting this as a proportional function of minus theta. Just like the case when in a translatory equilibrium, a translatory position of a stable equilibrium when the body is displaced, the restoring forces acting on it are directly proportional to displacement from mean position. So similarly here, if the restoring torque on body is directly proportional to the angular displacement, then this torque can be written as minus d theta, where d is just a proportionality constant. And if we find out the angular oscillation torque, we know that it can be written as I alpha, which is minus d theta, or angular oscillation we can write as minus d by I theta. Now we can compare it with the angular SHM equation for angular oscillation, in which we can write for SHM alpha can be written as minus omega square theta. On comparing the two, we'll get omega is equals to root of d by I. So time period of oscillation for the rigid body can be written as 2 pi by omega. It is 2 pi root of I by d. This is the way how we analyze the time period of a rigid body pivoted about the axis and it is under a stable equilibrium of some torques. Then the analysis is quite similar which we have followed for the translatory motion.